Great. Well, good morning, everybody. Thanks for coming back for day 2. So I'm going to start this morning by setting the stage of how the marshes that we looked at during the BWM project are responding to sea level rise. Before I do that, I just want to acknowledge all the people who helped make this project happen. They're listed up there, and specifically the coring field work was made possible by an intern through the NAGT, which is a USGS program, Kara Vadman, Priya Ganguly, Joe Kramer, Tom Kramer, former USGS employees, and then Jennifer O'Keefe-Suttles. I was funded through NSF, as Tana Marie mentioned, and the NOAA Nurse Collaborative and the USGS. So some marshes are resilient, and I know that's the R word that Steve Emmett-Maddox said to us yesterday, but that's something we really need to think about in terms of looking at these systems in a very dynamic environment that we have today. These have formed at the coastal ocean, which is itself a very dynamic environment. They have to deal with all the things that the coastal ocean can throw at them. And in addition to all of these, beautiful, wonderful things that the salt marshes provide, we're testing their resilience. We're testing that by looking at sea level rise, eutrophication, changing land use patterns. And so we're really testing their ability to provide these ecosystem services, and we're testing their resilience. And we're doing that in multiple ways. And the BWM project was excellent because it actually gave us a natural laboratory to test 2 of these things. One is nutrient input, which we're going to talk about later today, and the other is sea level rise. And how do marshes respond to this, and why are they so dynamic? And this is just telling you that the 2 processes that really control marsh growth, there's a biological processes and there's physical processes. And some promote marsh growth, and that is sediment accumulation. So that's the inorganic minerals as they come in with the tidal flow, the flow slows down and the minerals settle. And then there's the biologic part, production. They're very, very productive ecosystems. There's production above ground in the leaves, there's production below ground in the roots. Both of those will lead to a marsh growing vertically. And then there's processes that result in marsh loss of elevation. And those are really decomposition. So if you think about if you took a piece of fruit and you set it outside, it would lose its volume. It would collapse in on itself. And these marshes are excellent at prohibiting decomposition because they have an environment that is anoxic, and a lot of the electron acceptors that promote decomp are gone. And so, but that's one thing that can actually cause marsh loss. Lisa Marie mentioned some really amazing examples of it yesterday when she talked about how marshes were drained and then they became oxygenated and they basically lost huge amounts of elevation. And so that is happening naturally in marshes, but to a much lesser extent. And then there's erosion. So we have these processes promoting marsh growth, and then we have processes promoting loss of elevation. And so it's really this balancing act that this marsh is able to do in face of these kind of stressors that we're really interested in terms of what is the fate of blue carbon stored in these environments. So I mentioned we'll talk about nitrogen later, so what I'm going to highlight right now is sea level rise. All of you who are from New England know that we're in a place where sea level rise is actually quite rapid. It's above the global average. If you look at this trend, this is time on the x-axis, and this is mean sea level since 1932 at Woods Hole. So that's the closest NOAA tide gauge we have to the BWM site. And you're going to see there's an increase, but you'll also see that mean sea level doesn't increase in a straight line, even though we've thrown a straight line through it. The blue line is monthly mean sea level, and that goes up and down every year due to thermosteric effects. And then there's other oscillations through that. The gray line is a 5-year moving average, and you can see there's variability in that as well. And the reason I'm showing you this is you want to think, well, what time scale does a marsh really care about in terms of sea level rise? And so that's one thing that has come up looking at the data from the marshes and the BWM project. But overall, we've had a 2.8 millimeter per year rise since 1932. That's a lot. And so the question is, how have the marshes responded to this increase in sea level? One thing I want to point out before I show you any data is that current models of marsh growth, which we heard mentioned yesterday, really assume that 2 things happen, and it's the mineral accretion and this organic accretion. And the idea is that the mineral accretion is really driving the growth, and that's really, really important. And in fact, if you look at a lot of the the models of the paradigms, this is from Karan and McGonigal, they look at this sea level threshold beyond which a marsh can keep up with sea level rise or not is really dependent on sediment availability. And that's kind of the current paradigm right now, and that's based on a lot of work that has been done, in particular in marshes that aren't quite as organic rich as our marshes. So Waquoit Bay marshes have a low tidal range and they have a low sediment supply. We're not at the tail end of a river. And so these marshes are poised to maybe be what we would consider the canary in the coal mine. These marshes are predicted to be the most sensitive to sea level rise in the current model. And so what did we do? So these are the 4 sites that you've heard a lot about. These colors represent the marsh habitat, with the green, kind of the fluorescent green, is the low marsh area. And you can see our marshes are dominated by low marsh. There is some of the high marsh, which is a dark green, but that's a much less common ecosystem in this. And these nice stars represent where we've collected cores. There are 11 cores collected across the marshes. Only one of them here in Sage Lot was collected in a high marsh environment. The other 10 were collected in a low marsh environment. And how we collected these cores is we went out and we had a modified piston core. And the beauty of this is that you put a piston on the sediment surface and then you push a core down around it. Because the piston is held in place, we have a kind of a, looks like a sawhorse that holds the piston in place, and that allows that while you push this core down around it, the piston is holding the sediment in place, and so you're not compacting it. And so that's something that we looked at, and all of our cores were between 1.7 and 0.5 meters. And then we took them back to the USGS lab at Woods Hole. We sectioned them vertically, and we were able to take that sediment and we were able to then quantify radioisotopes to look at age, and then carbon. And so for those of you who aren't familiar with lead-210, I'm just going to give you a really quick primer. So lead-210 is the isotope, the radioisotope that we use to date these cores. And where it comes from is that there's a lot of uranium in the sediments. One of the decay products is radium-226. And anybody who has a basement in New England has probably heard about radon in your basement. So the decay product of radium-226 is radon, which is a gas. That evades out of the sediment into your basement, or in this case, into the atmosphere. And that has a very short half-life, days. And that decays to lead-210, which is not a gas, it's particle reactive. And so then it deposits either from rain or from dry deposition onto the surface of the marsh. As that is buried, it gives us a chronometer, so we can date different layers of the sediment. And so the assumptions that I've made in this model is that that supply of lead-210 is constant to the sediment, and that variability in lead-210 activities are due to variability in the accumulation rates and variability due to decay, which we know is well constrained. So in the end, we have 15 to 25 dated surfaces for each core. So I can tell you what the elevation of the marsh was at any time through the past, up to about 1900, which is about 5 half-lives of lead-210. And so that's what I'm going to show you next. So let me walk you through this. So the bottom is time, and the y-axis is elevation. And so this is now showing you the elevation of mean high water through time. So this starts at 1932, and this is mean sea level. And then this is the elevation of the marsh surface, and this is as far back as the lead-210 gives us. And there's 2 things I want you to see here. One is that these low marsh sites, so this is all 10 low marsh sites across all 4 marshes that we studied, they're definitely showing an upward trend. This is in line with the, the increase in sea level. However, it's not showing this multi-decadal variability that you see in the sea level record. So that's one thing I want you to know. The second thing I want you to know is this high marsh. The high marsh is definitely not on the same trajectory as the low marsh sites. So this is in line with what Serena has seen in the productivity at the high marsh versus the low marsh site. So really the fate of the high marsh is quite a bit different than the fate of the low marsh. And if we look at this not just as elevation through time, let me first state this pattern between the high marsh and the low marsh is exactly what we'd expect. Decades of research has shown that there's definitely a sweet spot for marsh productivity. So this is just one example of that, where they did a pipe organ. So marshes are growing at different elevations in the tidal frame. And the plot on the right is showing productivity. And you can see here, this is that sweet spot where the marsh grows the most. And because of this parabola, you see a lot of marshes trying to maintain their elevation within this zone. And so this isn't surprising to us that, you know, the marshes are falling below mean high water here, but mean sea level would be lower here. So, you know, these marshes are maintaining some position within the tidal frame that we would like them to. And what do these accumulation rates look like? So again, this is from 1900 here. These are all the cores. And you can see all of them are increasing, with the two that are increasing the least being this high marsh core in yellow here, and then this green core here at Great Pond. So all the others, they're showing very similar trends, which is good to see. So in terms of, what does this mean in terms of where they are within the tidal frame through time? So this next graph is a little more complicated. Let me walk you through. Same time frame. Now this is height above mean sea level. So this is their position within the tidal frame through time. And you can see here, this is back when we have data for the mean sea level, and you can see it's decreasing through time. So, and then right around 1970, something changed. And when I first looked at that, I thought, oh, that's the root depth. But it's not the root depth. The root depth is actually different in all these cores. It's between 10 and 20 centimeters. And right around 1970, these cores stopped losing elevation. And some of them are even now gaining elevation within the tidal frame. So this was actually something that's really good to see. The two losers in this game are this high marsh core, which is continuing to lose elevation within the tidal frame. And then this lowest low marsh core, that's the lowest elevation currently, low marsh core. And so there's some positive news. There is a response to sea level rise in these marshes, and they appear to now be responding positively. So what does that mean in terms of the carbon? So what has happened to carbon storage over this same time? So first I'm going to show you carbon density. So this is how much carbon is in the sediments, a certain volume of sediment. And what I'll have you know is that there's not a lot of vertical structure. And actually, if you go ahead and do the statistics, there's no statistical difference except for this one eel pond outlier here. All the other cores are statistically the same. There's no vertical structure. And this comes from the fact that the dry bulk density, which is the weight per volume, and the carbon fraction, the fraction of carbon that makes up these sediments is actually not showing any vertical structure either. This surprised me. I expected to see some structure in the root zone, but it's just not there. So this carbon density multiplied times the vertical growth rate is what gives you the carbon accretion rate. We already know the vertical growth rate is showing an increase. So when we look at that through time, we're going to see an increase with time. And that's what we're seeing right here. So this is carbon burial. This is in grams of carbon per meter squared per year. And you can see we started down here. These cores were anywhere between 50 and about 80 in 1900. And they're now increasing at the surface. So, and we're able to get these rates at each interval because we have accumulation rates at each interval. And so there's definitely been an increase there, although Eel Pond is showing now a decrease at the surface, but most of them are showing a general increase since 1900. And to show that even more graphically is this plot here. So green is 1950 to the present, average carbon accumulation rates. Brown is 1900 to 1950, and then 1900 to the very bottom of the peat. And in most places, I actually went all the way to the basal layer where the peat intercepts the sand aquifer that's under it. Those are the rates. And so you can see there's been an increase with time. And a part of this is going to be due to decomposition, but there's also, you know, we're not seeing any change in the physical properties of the sediments. There's no change in the amount of carbon. There's no change in the dry bulk density. So that's not the whole story going on here. And so what does this, schematically, what could be causing this? And I call this, so this is a little schematic of, this is the marsh here. And if we have sea level rise, here, we're creating this accommodation space. So basically, as the marsh grows, it wants to be in that sweet spot. And so as sea level rises and that sweet spot gets higher, it's actually creating the space where they can put down more sediment and accumulate more. And also the conditions there are then favorable for preservation of that. So they can actually have higher preservation rates as sea level rises as well. And so that's what's driving, we think, the increase in carbon burial. And so if we look at this, before I showed you those parabolas, so this is showing you the parabolas of carbon storage through time. And so this is the 1950 to 2014, which is when the cores were collected, average. And here's where mean high water was. And then this is the 1900 to 1950 average. The parabolas losing shape. And so something I've been thinking about is how is preservation going to be impacted by a location within the tidal frame? Because preservation and production both go into creating this plot. The plot before was just production. This is preservation plus production. And so the good news is that these cores are growing vertically faster. They've increased from 1 to 2 millimeters per year now to 3 to 5. So they look like they are, most part, keeping pace. The two that aren't are the high marsh cores and the lowest low marsh cores. And there appears to be a post-1970 bump in growth rate. And also storage of carbon has increased with that. So that's really what I have to tell you about the sea level rise impact on carbon. I was surprised. I thought these marshes would actually be suffering a lot more because other New England marshes in general, there's been a mixed bag whether they're able to keep up or not. So I was pleasantly surprised to see this, although it looks like the high marsh environment, which is actually supported by other work that's been done, is being converted to low marsh, essentially. And so, anyway, thank you for your attention.
Good morning. Good morning. Thank you for that presentation. So I'm wondering if your vertical growth rates that you determined on your sites, have you looked and compared these growth rates with other sites in, say, southern New England? Yeah,
so the method that I used for determining lead-210, so there's two ways to determine accumulation rates with lead-210. One is that you assume that there's a constant rate of growth, of vertical accretion. And with that, then you take the lead-210 values you get, you log transform them, and you fit a line to them. That allows you to get one vertical growth rate. And because of the life of lead-210, that vertical growth rate is the integrated rate from 1900. The way I calculated it is I assumed that there was a constant rate of lead-210 supply, not accretion rate, which means that I have to very accurately determine the lead-210 profile for each core. So I can't just take 5 or 6 points and count the activity and then draw a line through them. I take 30 points all the way down to the base of the layer. And so there's less data that have taken accumulation rates at this level. There's some. One notably is a Long Island Sound core, and they have actually seen really similar responses. And New York actually is experiencing very similar sea level rise rates as us, but there are fewer New England cores for me to compare with. And that's actually something that is on my agenda is to see if we can expand this and actually start looking. We know we're in this really, really dynamic period. And so the issue is how do we capture that with the tools that we have?
Okay, thanks. The reason I ask is because I'm familiar with some of the data in Narragansett Bay from the surface elevation table monitoring that's been done. And at least in the last 10 years, the vertical elevation gain on the marshes is only about 1.5 millimeter per year. And in the Newport tide gauge is almost exact increase since 1930. At Newport, it's 2.76 millimeter per year. So right there, and if you look at the last 20 years, it's actually closer to 4 millimeters per year. So clearly, the marshes in Narragansett Bay are not gaining elevation to keep up with sea level rise, and that contradicts what you're finding here?
Yeah, so I think the marsh response can get really complicated. So I know Rhode Island potentially has some other stressors that we don't have as high here. And I know the nitrogen story, to tell you the punchline for the nitrogen thing, we're not seeing a difference across the marshes, but it's possible that a higher level of load is going to negatively impact it. So I guess this gets to the tipping point, and that the tipping point might not just be a function of sediment supply, it might also be a function of all these other things that are decreasing marsh resilience. And so that's actually something I think we need to keep looking forward to, because if we're going to model which marshes are resilient and which marshes are going to survive, we need more data other than just it's about sediment supply.
Thanks, I really enjoyed your talk. One question, how do these marshes sit with respect to, Don Cahoon would always talk about elevational capital. So how high are they perched, and was that impact these rates of surface elevation gain that you have observed? So
when you say perched, do you mean in terms of what their elevation difference is between the channel? These are not perched very high. These are quite low. So you can see here, so this is mean sea level and this is mean high water. And so the tidal range is about a meter. And so, I mean, whoops, mean sea level is right here. They're not perched very high. Yeah, so but the issue is if once we get much more elevation, we switch to high marsh ecosystem. And the high marsh ecosystem can't accrete at the rate that the low marsh can. And so I think they have a fairly narrow range where they like to be. It's if they can keep up with where their narrow range is. And I was actually surprised to see that a lot of them appear to be doing that. I was very surprised by this, actually.
What you say that there's not the accumulation in the high marsh? It looks like there might be some, but do you know what the accumulation rate in the high marsh is?
I do. So I didn't mean there's no accumulation rate. I mean it's not going to keep up at the rate that sea level is keeping up. So the accumulation rates are here, and the high marsh site right here, it was around 1 back there, so they were actually quite similar in the past, and then now it's about half, and so it's right around 1.8 to 2. Yeah, and so it has increased.
Because the set might be monitoring the high marsh which would be a similar accumulation rate then.
Okay. Yeah, so no, the high marsh it appears to be the loser in this story, and so that talks for succession, and a lot of the conversion has actually been seen. There's a paper that just came out that was looking at conversion on Cape Cod, looking at a lot of the sites in Barnstable and some up in the National Seashore, and they're seeing conversion to low marsh settings, but the low marsh appears to be keeping up.
Hi, Meagan, very good presentation. I have a question about this figure. And you see that about 100 years ago, it's 1 to 2 millimeter per year, the increase of carbon. So have you considered the compaction effect? You know, the 100 years ago carbon is a little more deep, and the compaction effect may be more serious.
Yeah, so it's something that I'm thinking a lot about how to look at the compaction effect. The problem is a lot of the models assume that you have a steady state, and we're not at steady state by any means. And so it's really coming up with a way to think about that isn't at steady state, because we're not just at the same, as sea level's rising and as the marshes are responding to that, they're creating this new space where they can store that carbon. We're not seeing changes in the amount of carbon in the sediment, and we're not seeing changes in the sediment physical properties. So it's going to be harder to model the decomposition. Oh, so the compaction that Meagan is mentioning is that as it decays, it can lose soil volume. But a lot of times when that happens, you see an increase in the density of the soil, which we haven't seen.
Meagan, when we are talking about high marsh and low marsh, how high are the high marsh compared to the low marsh?
It's about 10 centimeters higher.
So in some point in the future, do they become low marsh?
Yes.
And in that case, do they have higher accretion rate?
Will they have the accretion rate that the low marsh has now?
Yes.
The thought is yes.
And then in that case, the conclusion that they're not keeping up, is that fairly accurate with the sea level rise?
Okay, so the high marsh ecosystem itself
Yes.
is not keeping up. The
But-
marsh as a whole
Okay.
appears to be keeping up.
But high marsh, at some point, if they become low marsh and they have an accretion rate like the low marsh, then maybe the conclusion would not be fully accurate, that they are not keeping up, right?
Yes, they're converting.
So my question was, when you were talking about keeping up, are you saying in the future, you may have less upland marsh as a percentage of the entire marsh, but you have the same area, roughly?
So that's what it looks like is happening on the Cape right now. And then making projections in the future really requires you to know what sea level rise rates are, which is uncertain, and two, what variability is actually important to the marsh. So we're seeing an increase, and so there's maybe suggestion that they can keep up, but is there something about the way sea level rises? I mean, this is something when I started looking at the sea level rise data, so I said 1970 is when they seem to start keeping up. So if you look here, look at the gray line. Do you see how, and it's actually not a lot of this 20-year, and by the way, this has got NAO removed from it, so NAO is not here. And then we start having these kind of large shifts on about a 10, 12-year time scale. Is it possible that the fact that it's going up and down and the marshes are getting some relief at some point, is maybe this is helping them keep up? It's just, I don't know. Right now I'm trying to figure out why 1970 was helpful for the marshes. But yeah, I do think that there's going to be conversion of high marsh to low marsh. And then total area is going to depend on whether the low marsh keeps up and whether they can spread inland at all, which is a topography issue and a land use issue.
Real quick, last question.
Yep.
Going down core, you said that there really wasn't a lot of change in the soil conditions. Any evidence of a change in vegetation communities? Did it look like it might be shifting into high marsh down low?
So I didn't show the C13 data, but it actually it doesn't look like it's shifting to high marsh until we get to the basal peat layer, which is where we get the sand, and then it looks like forest. All right, thank you.